Our scientific system of measurement, though not 100% the same as the metric system, is based on the metric system. It is used worldwide, pretty much in every country, and it is a system that treats all measurements the same way, which is why it's actually easier to use than the English system. In the English system, there's a lot to memorize. For example, 12 inches in a foot, 5,280 feet in a mile, 3 feet in a yard, 16 ounces in a pound, 2,000 pounds in a ton. There's a lot of different numbers at play, but in the SI system, everything is based on the number 10, which makes it a much easier system to switch from bigger or smaller units and to compare very different measurements, or at least understand very different measurements. The SI system is the international system, and it's designed to be practical and able to be duplicated everywhere in the world. Notice I didn't say easily duplicated, but still it can be duplicated anywhere in the world. For example, our definition of a meter is based on how far light travels in a certain very tiny fraction of a second. Since light travels the same rate in a vacuum, we can use light anywhere in the world to create the exact same distance of a meter. Our definition of a second is based on how many times a particular atom oscillates when you hit it with the laser light. Since that atom would behave the same everywhere in the world and probably everywhere in the universe, it gives us a definition of a second that could be duplicated anywhere. Now, it is made up of, or all of our scientific measurements are made up of two different types of measurements: our fundamental units and derived units. A fundamental unit is the most basic unit of measure that exists. There's only a handful of them. They are length, which is described based on meters. Mass, the fundamental unit for mass is the kilogram, because grams themselves are too small, so we use the kilogram to make it larger. Time is based on seconds. Temperature, here's where the SI system and the metric system differ. We don't use degrees Celsius in the scientific scale. We use Kelvin. Kelvin is based on the idea of absolute zero. There's an absolute coldest temperature that could exist. It's kind of theoretical, and that is 0 degrees Kelvin. The reason why we use this is because temperature is linked to energy. So as temperature drops in Celsius or Fahrenheit, eventually you have a negative temperature. Negative temperature almost implies negative energy. You can't have less than no energy. So Kelvin is based on the point of the lowest energy anything can have. The amount of the substance, biggie in chemistry, the mole, is a fundamental unit. And from physics, electric current and the brightness of a light are also fundamental units. Derived units are made up of more than one measurement. And this is a incomplete but pretty good list of derived units. Each of these is based on an equation mathematically that tells us how to get it. Like, for example, area in square meters is based on the idea that area equals length times width. So that's our two units of measure that are combined to get area. Volume is based on length times width times height, which would be measured in meters cubed. However, we like to simplify derived units the best we can to make them easier to describe and talk about. So we also use liters as a measure of volume. Now when you look at cubic meters, you can tell it's derived because you see meter, meter, meter. When you see liters, you just see an L. So we have to remember that that's based on a definition, and it's still made up of other measurements. Now, here is a definition that you should know. 1 milliliter is 1 cubic centimeter. In other words, we can define volume in milliliters as roughly the amount of space occupied by this small 1 cubic centimeter space. All right, other familiar derived units include speed, which is distance traveled in a certain amount of time, acceleration, which is a change in speed in a certain amount of time, force, which is based on Newton's second law of motion. Force is equal to mass times an acceleration. Work or energy, which is based on the idea of using a force to move an object a distance. Power, which is defined as the amount of work done in a certain amount of time. and pressure, which is a force applied to a certain area. Now, many of these units we simplify to make them easier. For example, new forces in newtons instead of using kilograms times meter per second squared. Work or energy is in joules. Watts is used for power, and pascals is used for pressure. Now, also on Google Classroom, you'll find a copy of all of the different prefixes in the metric system. Remember when you're looking at that list that all of the units that are to the left of the base unit are for larger measurements, and all of the units on the right side are for smaller measurements. So what does that mean? For these, larger measurements make the units, larger measurements make the actual number smaller. And over on this side, you use these for smaller measurements. And the reason why is they make the number larger. So you're not dealing with very tiny decimals, you're dealing with more manageable numbers. Now, as we begin to do conversions using the SI chart, we're going to be using the scientific notation for all of our conversions because it does make our life a little bit easier.